All right, we'll just let that record. Thanks, that'll work. All right, so we are doing day 2, which is a whole bunch of shading and fun. All right, so we have a bunch of vocabulary at the top. Did I give you a packet? A bunch of vocabulary at the top. Intersection, denoted by the letter N. Intersection. N. A and means A and B. Union means A or B. Complement means not A. And conditional means A given B. All right, so these are the formal definitions. This will be super important. So we're going to look at shading-wise what that means. So A intersect B means this. If you like colored pencils, now's a good colored pencil day. Also, A intersect B, here is all of this. So I would say this is still A and B. It just includes C as well. All right, remember that union means or. So this means or. This right here was and. Or means A or B. So this is going to be all of it. A or B here is going to be all of A, all of B. It's going to include parts of C, but not the bottom part of C. All right, not A, you're going to shade everything but A. Love the color. Over here, not A would just be all of this stuff. So it includes parts of C and parts of B. It just doesn't include any of A. All right, so A union B, but the complement. So this means not A or B. And we already know what we know what A union B is already from above. So you're just going to do the opposite of that. So not A or B is just everything around A and B. So it would just be everything in the rectangle outside the circles. Same thing here, everything but coloring, rainy day. Okay. Now we get into the conditional stuff. This is A given B. So focus on circle B and then in B, but also A. So that means A given B. So focus on circle B, which also includes A. So it's this or this.
So it's just the same thing as A and B?
That's what we're going to get to. In certain situations, yes. So this is not B given A, so we would focus on circle A, because that's what we're given. So in A, but also not in B. So that's kind of the visual representation of all of it. So now we're gonna look at it, that's in a visual form, now we're gonna look at it in a table. So we have a Venn diagram, we know that the probability of A, everything in circle A, is 7 out of 18. So the probability of not A, because we have 18 total, is just gonna be, what do we have left?
11.
Yeah, 11 out of 18. And the probability of A and not A should be the total circle. All right, so now we need the probability of B. How many things are in B? 9. So the probability of A plus the probability of B is 7 out of 18 plus 9 out of 18, or 16 out of 18.
So when you're adding A and B, you include the overlap for both?
Mm-hmm.
Okay.
So P of A union B is this, because it's the or. So it's 12 out of 18. And the intersect is the and, so that's just 4, it's what's in the middle. Then we've got P of A plus P of B, which we know is 16 out of 18, minus the intersect, which is 4 out of 18, which happens to be 12 out of 18. So we're gonna start to look for some patterns here. Does this just happen to match this? I don't know, maybe, let's see. Let's keep going and see what happens. Let's use a different color. All right, so in these two separate circles, this is a class of 2018 for whatever we're doing, the probability of A is just 3 out of 19. The probability of not A is 16 out of 19. And together that should be everything. Probability of B is just what's in circle B. It's 10 out of 19. A plus B, 13 out of 19. A union, in this case, they have no overlap, so it's 13 out of 19. It's just 4, so 10 plus 3. Intersect, they have no intersect, so it's 0. And then we take A plus B from column 5, which is 13 out of 19 minus 0, which is just going to be 13 out of 19. Now, the class of 2017 looks really funny. So the probability of A is all of that stuff. So it's 13. 10 plus 3. So we know just by subtraction that this has to be 6, because in total it has to be 19. And we know that together they add to 1. The probability of B is just the inner little circle, it's 10. Probability of A plus the probability of B. This is interesting, right? This is gonna be 13 out of 19 plus 10 out of 19. What's wrong with that problem? It's over 1. So we're going to talk about that. That's weird. The union is what do they have in common? They have 13. The intersect, they have 10. And then again, we just take whatever was here, 23 out of 19 minus 10 out of 19, and we get 13 out of 19. And we have our last circle. See if you can fill that in on your own, the last one. So when you're done, check it out. See if you got those right. Brady, will you shut the door for me? Thanks. All right, so what relationship in column, what relationship is shown in column 3? So in column 3, they always add to 1. And why is this relationship always true? Because something either happens or it doesn't. So your event's going to either happen or it's not going to happen, but together. Did column 5 and 6 always equal each other? 5 and 6? No. They did not always equal each other. All right, thanks.
Have a nice day, Miss Alco.
You too. What do you notice about columns 6 and 8? 6 and 8, are they always equal?
Yeah.
They sure are. They are always equal. And why is the relationship always true? The probability, Alex, will you shut the door for me?
Yeah.
Of A includes A intersect B, and so does the probability of B. So what does this mean? This means A intersect B is double counted during the probability of A plus the probability of B. Because you're counting it in A and you're counting it in B, right? So you're counting it twice. How can you tell that two events cannot both occur? That was when we had the probability of A intersect B being 0, or it was when the circles don't overlap. So that table might help you as we're kind of going through all this stuff. Okay, so part one discusses complementary events. That means that A and not A are mutually exclusive and some of their probabilities equal 1. You're killing me with the crack and knuckles. Part 2 discusses the probability of combined events, also known as the addition law of probability. And part 3 discusses mutually exclusive events that if A occurred, B cannot, and if B occurs, A cannot. So it's like you can't turn left and right at the same time. Those events are mutually exclusive. If you're driving a car, that's impossible. So this stuff is nice. It's in your formula booklet. So complementary events, the probability of something happening and the probability of it not happening will equal 1. Combined events is what we just did in the table. And then mutually exclusive is just that their unions, it's what their union is. So these probability laws can be used in calculating probabilities as well as justifying statements about combined events. So we're going to use these formulas because sometimes you don't have a diagram. So if the probability of F is 0.36 and the probability of B is 0.49, find the, and the union is 0.85, find the intersect. Well, you use this lovely formula in 4.6, which says the probability of F union B equals the probability of F plus the probability of B minus their intersection. Because we don't want to count the intersection twice. Sorry, I just called that A out of habit. Let's change that. And then it just becomes an algebra problem. So their union is 0.85, probability of F is 0.36, this is 0.49, minus the probability of the intersection. We algebra that up, we get 0.85 equals, ooh, interesting, 0.85 minus the probability of their intersection, and we end up with 0. So this means F and B are mutually exclusive. Yes.
Do you have tissues?
They're over here.
Thank you.
So if we were drawing that, F and B would be their own circles, they would not touch. So we would have F and B. Mutually exclusive. Can't happen together. No intersection. We good with just plugging in, following along? All right, there are 60 students that play football or basketball. All right, I have to write it. I like to write as I read, it just helps me. So football or basketball is 60. There are 40 that play football, so football is just 40, and 45 that play basketball. So we're gonna use the same thing we just used above. F union B equals F plus B minus, we wanna know the probability that they play both. So we're looking for the intersection. So that means that 25 play both. So that's how many kids play both, and that would be, if we wanted the probability of F intersect B, we would just do it out of the total and put that in our calculator and we'd get 0.417. So if it asked for, it didn't, Oh, it did. It says then what is the probability that the student plays both? Okay, so this is what we were looking for. So first you had to find out how many play both, and then we wanted the probability. So you can always get the union or the intersect if you have one or the other and each individual probability. All right, now we're going to go back to visual things. Independent and dependent. Independent is when the occurrence of each event does not affect in any way the occurrence of the other. Another way of saying that is that one event does not change the probability of the second event. So, drawing a marble and rolling a dice don't have anything to do with each other, right? But if I'm playing cards and I'm dealing cards without replacement, that's going to affect what my odds are of getting a certain hand, like if I'm playing poker. Dependent, basically two events are not independent, and we're going to look at how that looks. All right, so here we go with another Venn diagram. Same things as before. We're going to ask a couple different questions in the second part. So the probability of A given B. So you focus on B. There are 9 total things in B. And the overlap part is 4. So A given B. The probability of A times B is just from the first 2 columns, 7 out of 18 times 9 out of 18. And if you do that out, it reduces to 7 out of 36. The probability of A given B, which we just found, is 4 out of 9, times the probability of B. Well, that's lovely, because the 9's cancel, so we just get 4 out of 18. And yes, that reduces, but we're going to leave it like that for a minute. And then we've got the intersection, which is 4 out of 18, divided by the probability B, which is 9 out of 18. When you divide, you multiply by the reciprocal. I'm just going to come out, so that means 4 out of 18 times 18 out of 9. Our 18s cancel, and we're just left with 4 out of 9. All right, so interestingly enough, this matches this, and we will see what else matches or happens depending on, this right here happens to match this as well. So interesting. We'll see if that holds true for the rest of it. All right, this one's easy because you focus on circle B and see what the overlap of A is. Well, there's no overlap. Okay, and then we just multiply 3 out of 19 times 10 out of 19, and we get 30 out of 361. And then again, just plugging into the formulas is all I'm doing. So backing up from where that was just 0 out of 10 times the probability of B, which is 10 out of 19, is just 0. Ooh, they do match here though. This does match this. Interesting. All right, and then the intersection, which is 0, divided by the probability of B, which happened to be whatever it was, 10 out of 19. 0 divided by anything is 0. So we got all sorts of zeros there. So we got many matching columns, the same 4 columns. We got 0 here, we got 0 here, 0, 0. Okay. All right, so we've got the probability of A, the probability of B, their intersection, which is 10. Now we've got probability of A given B. Probability of A given B. So we're focusing on circle B, which is 10, which is also in circle A, so that's just 10 out of 10, which is 1.
10 out of 19.
No, this is 10. Okay, so again, like go back to the first one. So A given B, you focus on circle B, and then you take what part of it's in A. So we're taking circle B, the whole circle B is already in A. Does that make sense? A lot of visualization here. All right, so then we just multiply together here, 13 out of 19 times 10 out of 19, and we get what we got before, or something close to it, 130 out of 361. I guess it's a little different. And then the probability of A given B, which is 10 out of 10, times the probability of B, which is 10 out of 19. Is that right? Do I have the right thing? Yeah. 100 out of 190. A given B is 10 out of 10. B is, yeah, okay. And then intersect, A intersect B, go back to your other column. It's 10 out of 19 divided by the probability of B, which is 10 out of 19, which is 1. Huh. So this does match this. Which is that. Wait just a minute. Is anybody gonna correct my math back here, guys?
That's what I was
Yeah.
about to
I'm
say.
like, come on here. This was just 10 out of 19. Thank you. Grab a packet right there.
All right, thanks.
I'm like, somebody needs to correct my math. 10 out of 19. So this does match this. Feel free to, if I make a mistake, it's gonna happen.
So are we supposed to simplify?
You can, the purpose of this is just to see what lines up, so we're not, because it's what we're doing, but. All right, so last one, probability of A given B. So we're focusing on B, and the part that overlaps with is this. So we've got 5 out of 15. Then we just use all our numbers to continue on. So we've got 8 out of 24 times 15 out of 24, which is, that actually does simplify to 5 out of 24. And then A given B from column 4 is 5 out of 15 times the probability of B, 15 out of 24, which is also 5 out of 24. Then our last one, the intersect, which is 5 out of 24 divided by the probability of B, which is 15 out of 24. Again, multiply by the reciprocal, and you just end up with 5 out of 15.
Miss Alcock, I have a question.
Yeah.
So on the fourth column, for the second problem we did, for the, where we got 0 out of 18.
Yeah,
Wouldn't that be 0 out of 10?
maybe. Which one?
So it's for the, it's on the fourth column. Row. Fourth
Row.
Because it's
Fourth
A,
row.
B.
Yeah, where we got 0 over 18.
Oh, fourth column.
Yes, sorry. I've really never learned the difference between columns and rows.
Probability of A given B.
Yeah, and we got 0 over
Yep,
18.
should be 0 out of
over
10.
10.
100%. Thank you. Thank you. 0 out of 10. You are correct, because we were just looking at this here. Yes, thank you. Thank you. All right, did 3 and 6 always equal each other? Yes, they did. Did 3 and 5 always equal each other? No, only in the last one. When they do, it tells us something special. We'll get back to that. What do you notice between the relationships between columns 4 and 7? Those are also equal. So what that tells us is the probability of A given B is equal to the probability of A intersect B divided by the probability of B. That is gonna be an important idea. So you might wanna star that, box it, something like that. And off to the side, we can say this also explains why the probability of A given B times the probability of B equals the intersection. Because you cross multiply. That's where that comes from. That's where that relationship comes from. All right, so the exploration shows us how we calculate conditional probabilities, but it also shows us we can determine if two events are independent. This is important. If A and B are independent, then the probability of A given B will equal the probability of A. All right? Because, we'll just say because, B does not change the probability of A occurring. So that's what I was talking about. You have a marble and a die. Whatever my probability is of, or the spinner, let's say I have a spinner and a dice, whatever my probability is on the spinner is not going to affect my probability of rolling a dice. Doesn't matter. So that's what independent events are. So B will not change the probability of A occurring. All right, and again, these are in your formula booklet. Conditional probability, that's what we just discovered, and independent events, and you will use those. And people always forget that they're in there, and those are gonna be very handy, because one of IB's favorite questions is, are the events independent? So. All right, and remember that mutually exclusive and independent events are two very different ideas. Mutually exclusive cannot occur at the same time, so turning left and right when driving. All right, and independent events, one event does not change the probability the other event will occur. So like spinner and dice. All right, I think because we only have a couple more, we'll just finish this and we'll take like a little later lunch. I mean, we only have a couple more problems. All right, so suppose probability of C is 1/4 and the probability of D is 1/3. Find the probability of C union D if C and D are mutually exclusive. All right, so that would mean that the probability of C union D equals the probability of C. Back to that original formula that we used in the last examples. Write smaller. So what that means is the probability of C is 1/4, the probability of D is 1/3. If they're mutually exclusive, they cannot happen at the same time, so there's no intersect. So this means this. So we just make a pretty common denominator. We get 7 out of 12. Now, if C and D are independent, that means that the probability of C and D will equal the probability of C times the probability of D. So we can start by finding their union, just like we did, I'm gonna just draw a line. If I could get an eraser, there we go. Back to this formula. All right, so we would have 1/4, all right, I'll just rewrite it so it's underneath it, sorry. I'm trying to be, but okay. So probability of C union D equals the probability of C plus the probability of D minus the probability of C and D. All right, that's just from the left-hand side. So we're still looking for the union. So we've got 1/4 plus 1/3, but we're trying to see if they're independent. If they're independent, then P of C has to equal times P of C, B of D, multiply them together. So this, and this are all the same thing now. So we got our common denominator. We know that 7 out of 12 minus 1 out of 12 is 6 out of 12. So the probability of C union D is 1/2. So those are the two different types of question you'd be asked. Okay, find the union if they're mutually exclusive, find the union if they're independent. The highlighted parts are the key parts of what you need to know for that. All right, and then this is a lovely IB question. Given that P of E equals something, P of F equals something, and their union equals something, are they independent? All right, so basically what we need to show that the probability of E times the probability of F equals the probability of E intersect, not B, F. That goes back to the formula right here. Independent events. So their intersection should equal each one multiplied together. So we know that the probability of E times the probability of F is 0.4 times 0.5, which is just 0.2. And then we use that long formula to get the intersect. So the union equals the probability of each one added together minus the probability of the intersection. We're given the union. We know each individual probability. So 0.7 equals 0.9 minus the probability of the intersection. Bring it to the other side. 0.2 equals the probability of E intersect F. So these are equal, which is what we were going for. This equals this. Equal. So yes. Independent. So you're really just using 3 formulas over and over and over again. You're using that the individual properties multiplied together equals the intersect. You're using the intersect equals each one added together minus the intersect, or the union equals each one added together minus the intersect, and then the conditional one, which is up there. All right, last problem. Okay, Rosewood College has 120 students total. That means 120 students total. The students can join the sports club S, the music club M, for a student chosen at random from these 120. The probability that they joined both is 1/4. And the probability that they joined music is 1/3. All right, so we're gonna do this. We're gonna do both. So the probability that they join both is a fourth of our total. And the probability that they join music is a third of our total. All right, so 30 for both and 40 for music. All right, both we know goes in the middle. So this is always the intersect or both. So this is right, like, this is music intersect. That's what that is right there. There are 20 students that didn't join, so that's outside the circle. So music only. Music only is what? Does anybody know off the top of their head? 10. Good job. 40 minus 30. So music only is 10. Good job. And then we gotta know what sports only is, and we can just do a whole lot of subtracting to see what we have left. So we would do 120, we know we got 30, we got 10, and we know we got 20 outside. And that gives us 60. So now we have all the pieces and parts to answer all the fun questions. So getting the diagram correct is half the battle. And then we'll answer these two questions. One of the students who joined the sports club is chosen at random. Joined the sports club. Okay, so we're just talking about the sports club. Find the probability that this student joined both clubs. All right, so the probability that the student is in both clubs. So that's the overlap. The probability would be 30 out of, there are 90 kids in club, 90 kids in the sports club. So this is basically, this is a conditional probability known as given 90 students. One of the students who joined the sports club. So that's where the 90 comes from. So given that 90 students, that's what becomes the denominator. Find the probability the student joined both. So both is the intersect, so 30 divided by 90, and you get a third. Just be very careful with the wording. Determine whether they are independent. All right, so we're gonna show that the probability of sports times the probability of music is gonna equal the probability of sports and music. So probability of sports is 90 out of 120. The probability of music, now remember it includes the overlap, times 40 out of 120. Does that equal 30 out of 120? This is what we're trying to prove. So basically 9 out of 12 times 4 out of 12, which we can still reduce. Does that equal 3 out of 12? So 3 goes into here 3 times, 3 goes into here 4 times, 4 goes into here 1 time, 3 times. So we end up with 3 out of 12 equals 3 out of 12. Or you put it in a calculator, and yes, it does. So yes, they are independent. So I think the most challenging thing about this unit is the wordiness of it. It's like the and, the if, given that, both, some, one, union, stuff. So, you guys can go to lunch, come back at 1, and then we will work on the assignment and see how it goes.